end in time for thank you for everyone for coming to this, the 16th hour of lecture this week already. I hope you will accomplish just by this. So today what I want to do is sort of explain why I put you through the last 3 lectures, sort of what the motivating project was. And our motivation was to make this thing called the quantum A-polynomial. What I'll do is I'll start off by explaining what the A-polynomial is. Okay, and then I'll start talking about this, how we make a version of it. So, we'll start. Here's the A-polynomial, and just because this is sort of an embarrassing thing to try to do Google search, I'll give you a reference. Living in S3, and this is just a way of making a polynomial associated to that. It's something mathematicians love to do. And the construction, the basic idea is that you can start by thinking of RG, so this representation variety, of S3 minus this embedded knot. And here, this is already a knot invariant, right? So it just depends on the knot, but it's not what we want. We want something more concise. So we want something that's a little shorter, smaller information. And you could say it's simpler. And in order to do this, what this group of people did is they used 2 tools. The first tool that they used, which will be a little familiar, is one they used the fact that inside this group G, once I've picked a Borel, then I can consider the maximal torus, this thing T. And this is abelian. So whatever construction I can make with G, if I can move it over to T, it's going to be simpler for me to work with. So that's one tool. And then the other tool that they're going to use, we'll see, is you use the boundary torus. So you use the fact that if I take the boundary of S3 minus this knot, so maybe minus an open neighborhood of this knot, this is going to look like T, the torus, and this embeds into my knot complement like this. I don't want to write about that. So how does this show up? This I talked about a bunch yesterday, so you can imagine how it might appear later. But how this is going to work is that this thing's fundamental group is just V2. Right? And I can map from here this fundamental group to this fundamental group. And what I'm going to do is I'm going to just say that some choice of generators here are going to be sent to L and M. So this L and M is what I'm going to call my generators. Actually, I'll call them uppercase. I want to use lowercase for something else. Cool. So L and M will be the image of this map for the construction. Okay. And so how does this sort of map relate to the representation varieties? Well, remember, representation varieties are maps out of the fundamental group. So this is going to induce, if I call this thing J, this is going to induce something from representation variety is not complement to the representation variety of the torus. Like that. So this would be the other ingredient that we use. So now, this is just means G some reductive group and B some Borel, but I want to talk about their actual construction. So what I'll say is, say G SL2C. This is what the original construction is for. You could go through it with other reductive groups. Otherwise, we might get more than one polynomial. Cool. So if you see this construction and you think, what if I wanted to do it for SL4? You could do a lot of it, but that's one thing that would go wrong. Okay, let's talk about what the construction is. And the construction of this A polynomial. So my first step, so what I'll do is I consider this RG of S3 minus K. And inside there, I want to define a subset that I care about. So it'll be representations S3 minus K into G. And I want ones such that when I look at them just on this L and this M, this lies in some Borel. And just to make this precise, this is going to be the Borel of matrices that look like that. So I want to consider this space. Let me give this space a name. I'll call it sort of a fancy V. So once I have this space, the next step that I can do, so here you can see we're already using the Borel and the boundary. The next thing I'll do is I'll call it the eigenvalue map. I'll call this psi. And what it will do is, well, if I go from V, I can take the restriction of this map here, right? So I'll restrict to the subspace fancy V in here, and I go to RG of pi, like this. So what this is going to do is I can think of, if I have some row here, all I need to know is what it looks like on the generators here. So I'll get something that looks like lambda inverse something mu inverse something like this. Right? So I just need this representation here, I just need to know what it does on the generators of the fundamental group. And then next what I'll do is I'll go to T of pi. So T, because we're in SL2, is just diagonal matrices. And what this is going to do is it's going to forget that other entry. So like this. Just like that. And altogether, I'll call this map psi. Put that on the board. This whole map. This is what I mean by psi. Okay. So here I've done two kind of simplifying steps. I only want to consider representations. I have a nice form on these two elements. And now I'm just projecting and remembering the diagonals. And what I want to do, because I will want to build a polynomial, is my third step is going to be to build a module. What's my module going to be? Well, I'll take the image of my nice subspace inside of RT, the torus. Let's think a little bit what this looks like here. So yesterday I talked about RG of the torus, G some reductive group. And I knew that it was pairs of elements inside there, such that AB equals BA, like this. But now this here this is always true. In T, because it's commutative, so this space is just two copies of T. So T cross T. And because I'm working with SL2, T is my maximal torus is just diagonal matrices. I know it has to be something, some invertible element, and it's inverse. So this is just going to look like C star cross C star. So all the complex numbers except for 0. Are there questions on this? Okay. So I've defined a subspace. What you can do once you define a subspace is you can build a module like this. C star is going to act on this subspace. Like that. And what is this? Well, I'm looking at regular functions on C star cross C star. You might have seen before, if you've taken some algebraic geometry, that this, if I look down just C squared, this regular functions, that they are going to look like polynomials in 2 variables. But here, because I don't have 0, I have 2 invertible variables. So this ring is going to look like Laurent polynomials in 2 variables. Another algebraic geometry fact is that this thing, so this is looking like this, and this is going to look like that same ring modded out by some ideal, and that ideal is going to be principal, like this. So this is just what this module that I built looks like. So here's the definition from this paper, SCGCS 94. So the definition is the generator of this ideal normalized to have leading coefficient 1 is the A-polynomial. Cool. So that's my definition. This normalization thing, I need it because if you define something as a generator of an ideal, it's only defined up to multiplication by invertible elements. Let me switch the words. So you have to say what the, sort of which one. Okay. So here it is. I moved the board, but let me just write down a couple of examples of what these look like. So for the unknot, this will look like L minus 1. And for the figure 8, this looks like an actual longer polynomial. M to the 4th plus L times minus 1 plus M squared plus 2 to 10 to the 4th plus 10 to the 6th. And then plus L squared.
Jenny?
Yeah.
So O-polynomial is just a Cm plus minus 1. I mean, it looks like A just L.
No, A then will not just be L. Oh, so for the unknot, A is L minus 1. And for the figure 8, it's this longer thing. Is that your question?
What is different than A and RT? Is same A with RT?
Oh, no, sorry. No, I used A and B again. This A is not I. I just accidentally used the capital letter A twice. I'm sorry, everyone. All right, so here it is.
They're not normalized.
What?
They're not normalized as you said.
Oh, are they not?
I don't know. The leading coefficient should be 1.
Oh, yeah, it's minus 1 here. Yeah, that's right.
There is some.
Here's the problem is, yeah. Thank you.
Yeah.
Oh no, this is the
No,
plus
there is
thing.
no. There is no leading one, right?
This is the, yeah.
Above as well, right?
Oh my goodness.
Okay, okay, but it doesn't matter.
It's not changing. So what I'll say, and this is actually a good question, just to be warned, if you look online, there are many different conventions
Okay, yes, you're not
for
sure.
this.
Okay.
And one of them is that L, some people use L and some people use minus L. That's one. Another one is some people get rid of repeated factors, some people don't. Some people always multiply it by this, some people never multiply it by this. So there's a lot of different versions of the A-polynomial that are all different and uninteresting, horrible, terrifying ways. Okay, so I want to say, why were we interested in this? This not invariant from the 90s. Besides just it's nice, we like to have not invariants. So here's the motivation. And this is in my paper with David Jordan. This is like the motivation behind that long project. Is that we want to give a Skein theoretic quantization of this thing. And I want to say what we want to do in particular is we want to generalize a construction that Tudor made that's really nice from 2001, or sorry, 2011, that used hyperbolic geometry. So we want to do that. Why do we want to do that? Well, we want to do this thing because there's a conjecture. And the conjecture is if I take another really famous not invariant called the colored Jones. And I look at its recursion relations, which is to say I look at some annihilation ideal. Which is an ideal in some ring that just tells me what's all the recursive behavior of this thing. This should be an ideal that's generated by a quantization of the A-polynomial. So here's the conjecture. This is called the AJ conjecture, because one consequence of it is that if you take this AQ and you act on J, you get 0, so it's AJ. That's very nice. And this was made, this was sort of crystallized by Diophanidis in 2005. And then independently, there was a physical interpretation coming from the same, roughly the same conjecture by Sergei Gukov in 2006. And these conjectures are still open, even though they're going on 20 years old now. They've been solved for like some families of knots. People will take some family of knots and they will drive themselves insane studying them until they dream about them. So they've been studied and solved in some cases, but there's no general solution. So what we were thinking is if we gave a Skein theoretic quantization and the Collier-Jones polynomial is defined in that same Skein theory, this will help understand why this is true. So that's our motivation behind it. Other questions? I know it's really warm and really close to lunch. It's hard to ask questions. No worries. So now what I want to do is talk about what is that construction, which is these things I'm erasing. Now I'll try to rewrite them all, but in a Skein theoretic way. Okay. I also want to say one of my favorite things about this conjecture, just historically, is that when people first saw the A-polynomial, one of the things they were really excited about is it wasn't related to the color-Jones polynomial. Because it's hard at that time, I guess, to make polynomials not related to this, and now we're really excited because it is in fact related.
How could prove this conjecture?
Oh, if we have time, I can talk about how this work would help prove it. But it's not like a small step, following what I'm explaining. Okay. So what's the Skein theoretic description? Well, let's just go through all of the objects that showed up in this A-polynomial construction and start writing down what they look like Skein theoretically. So we have this space here. And yesterday, during the geometry section of this talk, I made the argument, and I talked through some of the details, that this thing is going to be quantized by the Skein algebra with coefficients in rep qt of the torus. One thing I didn't discuss, but if I want to do the representation variety here, I need to use the internal Skein algebra here. And this thing is a pretty nice form. This is generated by, I'll call them L and M, L and Q, M, L. So this will be the longitude meridian of this dot. And because I will say this thing a lot, use this a lot, let's call this blackboard bolt W. And it goes by the name bioalgebra. Actually, the Q algebra. So it's some deformation quantization, or some Q difference version of this. Okay, so we have this. Next thing I may want to quantize is on this RT pi, I can act on these functions on the space V. Right? So I've erased it, but I made some subspace fancy V. And I'll say this is an action via the map, this eigenvalue map, going from OV to O of RT. Right? So whenever I have a map between two rings, I get an action like this. And what is this going to become? This is going to become, well, I know what happens with the torus. This is the internal Skein algebra of Qt with the torus. And this is going to be acting on something I will module of M tilde. So let me draw what this manifold is now. And let me, in fact, draw it so I have a lot of space. Something I didn't explain yesterday is that there's also an internal version of the Skein modules. You also can have things in. I didn't tell you how that works, but it also works. But now what I will tell you is what this space is that I'm looking at. I don't want to draw it really big because we'll be looking at it for a little while. Okay. So what I'll do is I'll start with my knot, and I'll leave space above this and below it. Oh, that. And like that. Like this. So I'll take my knot, and now let me draw a little cartoon picture of S3 minus my knot. Right? So this is kind of a cartoon. And I know that I want here to be acting by some rep. So here I just have a torus, and I want it to be colored by T, and I want it to act. So I want this part to be T, but when I was defining the polynomial, I started off with the G variety, so I also want G in there. And actually how I'm going to do this is I'll put a Borel defect here. So this is the Borel, the parabolic defect. And it's going to look like just a copy of the torus that's parallel to this knot, what this cartoon means. And so now if I look here at this part, this is this knot complement. And just to orient ourselves, this part here, where I go from this little neighborhood, this defect here, this is going to look like the torus times some line like this, where I have T here and G here. So it'll be like a thickened torus that's like a T thickened torus and a G thickened torus connected together on a defect, like that. So this whole thing here is my MK. Okay. So what's going on? Well, here, right, I have the right type of module because I'm acting by a torus, that's curled by T. And here, what am I doing for myself with this defect? The argument is that this whole part here implements both this restriction in the Borel and this projection. Because somehow when I get close to the torus, I need to be in my Borel, and then actually when I'm thinking about this action, I demand that I'm actually in my maximal torus. Okay. So this is this step here. There's one more little step that happens, which is that this is not quite the module that they use in their construction. Their module that they're using is RT acting instead on the image of V, like that. So you can see it's a little different, act on the image of this map versus acting via this map. And this is just restrict to the submodule generated by the entity. So somehow restricting to the submodule generated by the entity is restricting to the image of the map that I'm acting by. And when I put this all together, what I get is this Qubal algebra acting on the submodule. This is the submodule generated by the empty. And what I'll have here is that this looks like the Qubal algebra modded out by some ideal. Just because this is a surjective map from V to its cyclic submodule. And my definition, just to mirror what they had before, is, so here's def, the quantum A-polynomials. So here, we're not guaranteed that it's a principal ideal, as far as we understand. So the multiple are generators. We also haven't settled on good, like if you can pick different generators, you may not agree exactly what these are, but you should think of the actual invariant is this ideal. Okay. Other questions? Okay, so we did that. here's the theorem, also from the paper. Is when the Q goes to one limit. Actually, we go Q 1/2, this is -1. AK goes to the classical A ideal. So just the classical ideal generated by the A polynomial. Okay. We made a construction. What I would like to do now is give an example of what it might look like. And let's just do the first example. The nicest knot to draw is, let's just think for the unknot. What does this look like? So first off, this mk tilde. So this is going to be the complement of an unknot with this nice stratification. So this is going to be actually just a solid torus. And this solid torus is going to, so if I think of my torus as a disk across S1, well now I have a stratification. And the stratification is like this. There's a G region in here and a T region out here. And I have my defect like that. Okay. So what I want to do is I need to start thinking about what's this looking like, right? And first, one thing I want to note that's useful is that pi1 of this just a solid torus is just Z, and it's generated by the meridian. Right? And so the meridian here is going to look like, if I looked at it in this cross section, it's just going to look like a dot here. So this is, the meridian is going to be this circle we can't see. Or I guess this circle. Okay. Yesterday, what we saw is that if I take in here my defect, and I look at this thing, so now this one, so this is all going to be across the circle, but I'll stop writing cross circle. So this thing here will be the longitude, right? And it's inside the G region, so I'll call it L sub G. And we saw that in a localization, this is going to look like this plus this. L inverse. And let's call these things L. This one L inverse. Right? And I'll say I've been really rude about using notation, but here when I say this L and L inverse, this really is this L and L inverse, right? If I act by this internal Skein algebra on the boundary, what it's going to do is it's going to be looking like putting in more skeins from the outside. So this is actually what would, if I act by L or L inverse, I would get this and this. So like that. So yesterday we saw that. This is contractible, this loop. So this is going to look like Q plus Q inverse. Nothing there. So this and this being equal, what this means, and this is true in my thickened torus, the Skein module of my thickened torus. What this means is that my ideal I sub k is going to look like L plus L inverse minus Q minus Q inverse, and that I can factor, multiply through by L, and factor it, and this will just be L minus Q times L minus Q inverse. Move that up. So you see, when I take the classical limit, what I'm going to get is L minus 1 squared. And this is the thing I was warning you about, is depending on who's writing down the A-polynomial, they may take squares of factors or cubes of factors or not. So we really get this unreduced version. I'll say it could be nice if I did the computation of the figure 8 polynomial, but now I will say that it's not easy to compute this thing unless you're computing it for the easiest example. And if you are curious for personal reasons how to do it, I would say 80% of the work on the paper is giving a way of computing these things. That's like the big thing, is how to approximate it. It's not trivial. Okay. Are there questions? We're doing well on time, so we will have lunch on time even if there are questions. So now what I want to talk about is how this whole thing has anything to do with this HA conjecture that I said was our motivation. Sort of how this would, the next thing that you would do with it, which is sort of relate it to these recursion relations of the Color-Jones polynomial. Okay. So how do we make the Color-Jones polynomial? Well, I'll tell you now. What happens is I take S3 and I insert my knot. Like that. And the Color-Jones polynomial depends on a parameter n. What I do is I take this skein and I color it by n, the nth dimensional interrupt of SL2C, like this. And because this knot is not interacting, there's no topology for it to interact with, I can evaluate it out using my Roche-Tikin derive thing, and I will get it some scalar. And so I'll just call this K so I don't commit all of us to drawing the trefoil too many times. This is just K Vn, some scalar, times just the empty thing, like this. And this scalar, after normalization, is the Color-Jones polynomial at n. So this is how it's built, very, very rapidly. And what we wanted to do is we want to consider this action of the Weyl algebra, JK, like this. And how does this work? Well, this Q-Weyl algebra, it has two generators, so I can tell you the action just by telling you how those act. What I'll do is L of this thing will be J of K n plus 1, and M JK of n equals Q Vn J A of this. And the annihilator ideal is what it's going to be the kernel of this map. So JK is the kernel So here's the ideal that we care about, which is just to say anything in here when it acts on J is 0. And what you need to do is you need to understand this action in terms of also Skein modules. We got another big picture. For this, and then I think after that that'll be the good finale thing to draw. So what's going on? How do I understand this action? Well, what I want to do is in the end, I want to have just my knot inside my thing. Let me see how did I draw it? Okay. So I know in the middle, I want an action of my torus. And what I'll do is on one side, this action will be on, let me draw my notebook so I can draw it. Here it'll be on this solid torus we've seen already, sort of in a different context. This solid torus, I'll just draw it and I'll explain what it is. So what's going on here? If I take a cross section, what this looks like is I have my outside T region, and I have this G region, and I have K like this. So this is K, and this is my Borel defect. So this is what's being turned around a circle to make this. And then on the other side, the action I want to have is the one that incorporates my knot. Like that. So it'll be this space that we've seen already until the K with this defect that we saw, like that. And the idea here is that the L and M that are acting there are exactly this L and M here. Maybe I'll draw them in orange. So it's the action by this element L is that thing, and the action by this element M is that. Right? And on this side, it's what I use to make my quantum A-polynomial. And so when I glue it together, when I compose all of these things, what I'm going to get is a copy of S3 with this this trefoil. Here, I'll just draw it kind of in a way that makes it clear that it's complicated, and then I'll zoom in and say what it looks like. Like this. Where here, what's going on, if I take a little cross section and I look at it, is I get two parallel defects, like that, and then in the middle K. Right. So what I have here is a little T region that's a knotted torus surrounding my knot, and maybe I'll draw what these look like. So acting by L is going to look like a parallel copy of K, but inside the T region, and acting by M will look like adding a little meridian to the knot. And the theorem that you would need to show, which is a statement about invertibility of defects, is that this is the same thing as just my knot, here like this. Like that. And say I acted by just L, this would be the knot colored by, say, B n plus 1. I acted by n, then it would be q to the n plus that. Okay, so that's how you relate. And what you need to show is that the kernel of this map is exactly capturing the kernel of going from this action to this whole colored area. That's where one stops.